Good evening, everyone. Welcome to problem solving session, week 6 of Theory of Computation. So, this week's topic is Turing machines and decidability. Turing machines and decidability. So, before I deal with some questions on decidability and do a short recap on Turing machines, I will discuss just two questions based on the previous assignment, that is week 5. Okay, so let us begin. So this is assignment discussion. Okay, so the question says, uh, okay, consider the language L W such that W has an equal number of A, B, C. So here we can see that, okay, here we can see that sigma has A, B, C, the alphabet, right? And okay, next, L of n. Okay, this is the first language, which is called L. Next, L of n is a to the n, b to the n, c to the n, and L2 is W such that W is in A star, B star, C star. Okay, so immediately, okay, first let's see what the question says. Pick the arguments that are true. An option is correct. Both the arguments and the conclusion derived in the option must be correct. Yeah. So next, let's look at the options. First one is the language L is regular, hence it is also context free. Well, this of course does not make sense because uh, the regular language sit inside context free language. So all regular languages are context free, and hence it does not make sense to say. Oh, sorry. It does make sense. Uh, the fact that a language is regular also means that it is context free. It is saying the language capital L is regular. Okay, what is capital L? W such that W has an equal number of A's, B's, and C's. Now, on face value itself, this language does not seem very regular. We have not seen any DFA that would recognize such kind of language. Okay, and this does not appear to be regular. But of course, I mean, there are a lot of tricky languages whose definition makes us feel that uh, uh, whose definition makes us feel that way, that it is not regular. It is regular, but in fact it is not. So let's see. Uh, W says that W has an equal number of A, B, C, right? So one way to disprove this would be using pumping lemma. Okay, choose something like A to the P, B to the B to the P, C to the P. Now this guy has an equal number of A's, equal number of B's, and equal number of C's. And by the pumping lemma, xy is at most of size P, right? The length of xy is at size of at most P, and therefore y consists only of A's. Right? Now, you should pump y. That's what the pumping lemma says, right? And this guy is in the language L, right? And let's assume that L is regular. That's how we do it in pumping lemma. If you assume that L is regular and P is the pumping length given by the pumping lemma, then pumping lemma says that no matter how many times I pump y, the string will still be in the language, right? So if we pump y's, okay, we get A to the P And let's say consists only of a's, right? Y consists only of a's. Let's say y equals um, a to the k. Then if we pump y's, x, y square, z, if we do that, and this part is z, then what do you get? X is um, some xy is totally a to the p, and if you add one more y, then you have k more a's. So there you get a p plus k, b to the p, c to the p. And since y cannot be empty, this k is greater than equal to 1, right? And therefore, according to pumping lemma, this should be inside L. This should be inside the language L. But clearly this is not inside L. Clearly this is not in L. But which this violates pumping lemma. Pumping lemma would not have been violated if pumping lemma would not be violated if L was actually regular. So this shows us that L is not regular after all. Okay. So language L is regular is out of question. So option A is wrong. Let's look at the next one. The language L2 equals all those strings where A star, B star, C star, W is in A star, B star, C star is context free. Oh, okay, sorry. The next one is the language L is not regular. Okay, L is not regular. Okay, that makes sense because here it means L is not regular, right? So L is not regular, but what is the reason they give? Because the language Ln is not regular, this is a subset of L, and this is a subset of L. Let's see. A language L is not regular because the language Ln a to the n, b to the n, c a to the n is not regular. This is true. This statement is true. We've seen that this, in fact, this is not even DCFL, deterministic context free language, right? And this is true. This language a to the n, b to the n, c to the n is very difficult to compute, right? It's not regular. That is true. And this is a subset of L. Does it make sense? Is it enough to say that? So let's look at option B. What option B means is, okay, the language L is not regular because the language Ln, okay, the language L is not regular because the language Ln is a subset. And since Ln is not regular, then L is also not regular. That is what it's saying. Is that true? Well, this can never be true. Okay. Okay. Hi, someone has just joined. I'll repeat the question. There are three languages given to us. A string which has an equal number of ABC, and a string which has equal number of A, B, C, but they are in sequence. Okay, A to the n, B to the n, C to the n. And L2 is all the strings which are of the form A star, B star, C star. So this one is clearly regular. This one is clearly regular. And the question says the following: the language L is regular, hence it is also context free. So firstly, what is L? L is this equal number of A's, B's, and C. Oh, hello. Hi, Bhavana, can you hear me? Really sorry, I had put my mic on mute. Now can you hear me? Hello? Hello? Oh, okay, okay. Yeah, okay. I saw your chat. Okay, good. Thanks. It seems there was a miscommunication on the timing. I think it got mixed up with the rescheduling last time. So people didn't get notified probably, it seems. But thank you for showing up. uh, okay, so let's see. Yeah. So Buana, there are three languages given to us. Okay, equal number of A, B. So I'll be discussing two questions from the previous assignment. Then we'll move on to this week's content. Okay. So the previous week's assignment said that there is this a language which has equal number of A's, B's, C's, and ln is A to the n, B to the n, C to the n, and L2 is A star, B star, C star. So this L2, okay, this guy L2 is represented using a regular expression. So definitely L2 is regular. Okay. So let's see what about the others. Okay. Okay. So the first one, it says pick the arguments that are true. Okay. The first one says the language L is regular, hence it is also context free. Well, first of all, is it true that if your language is regular, it is also context free? The answer is yes. Every regular language is inside a CFL. Okay. Why? Because any DFA can be simulated by a PDA without using the stack, because PDA is more powerful. It has a stack. If it decides not to use the stack, it can do anything that a DFA can do. So regular languages clearly under CFL. So in that way, it makes sense to say if a language L is regular, it is also context free. But it is talking about this particular L. The L it talks about is this guy. W says that W has an equal number of ABCs. This language, is it regular? That is the question first. And the answer is that it is not actually regular, because we can use the pumping lemma to disprove that it is regular. Okay. How do you do that? Well, take, say, for example, A to the P, B to the P, C to the P. If this language was regular, then pumping lemma says, oh, you can actually split it into X, Y, and Z, where X, Y is at most P, length at most P. So if X, Y is of length at most P, then X, Y is entirely consisting of A to the P, A's. Or in other words, Y consists only of A's. Y consists only of A's. So let's say Y is some A to the K. Pumping lemma says if you pump Y, okay, and let's say I do XY square, then I get more number of A's than B's and C's. And according to pumping lemma, this should be in the language if the language was regular. But clearly this is not in the language, because number of A's, B's, and C's are not equal. So therefore L is not regular. Okay, so option A is not an option at all for us. Let's look at the next option. Okay, a language L is not regular because the language ln equals A to the n, B to the n, C to the n is not regular, and this is a subset of L. Okay, it is saying L is not regular because ln is a subset of L. Ln is a subset of L, and since ln is not regular, L is not regular. Okay, does that make sense? Can we get a counter example of this fact? That is the question. The smaller set is not regular, but can it be that the larger set is regular? Do you have any counter example for that? Can you talk about a smaller set which is not regular, but a larger set which is regular? Okay. Or in other words, what is the largest language that you can construct in some sense? This is visible, right? What I'm writing. Is this visible? Yes. Okay. Okay. So it's visible, right? Okay. Okay. So if you look at sigma star, sigma star, is it regular? Yes. You can always construct a DFE that accepts all strings, right? Just looks like this. Sigma star is regular. But a to the n, b to the n, is it regular? This is one of the most popular examples of a non-regular language. And clearly, a to the n, b to the n is a subset. The language of a to the n, b to the n is a subset of sigma star. Everything is a subset of sigma star. And but this guy is regular, and this guy is not regular. So there is clearly a counterexample for what they are claiming. It is not true that when I have a subset which is not regular, the bigger set should also be not regular. Okay. So their claim does not make sense. Option B does not make sense. Option B is false. Okay. Let me copy the. Okay. Okay. I hope it's clear so far. Please let me know. So next they are saying the language L2 is context free. The language L2, W in A star, B star, C star is context free. So is this true? Well, A star, B star, C star is already regular, and any regular language is context free. Like I said, regular language is nothing but those which have DFAs. Context free languages are nothing but those which have PDAs. And PDAs are nothing but a DFAs with stack. And if you anything that can be computed by DFA can be computed by a PDA, because you just don't use the stack at all. You just don't use the stack at all, and it is as powerful as a DFA. So if A to the B, A star, B star, C star is regular, then it is also context free. Okay, so option C is correct. Okay, now let's see. The language L intersection L2 is LN, and LN is not regular, therefore L is not context free. So let's see. L intersection L2. What is L? L is W such that W has equal number of A, B, C. And L2 is A star followed by B star followed by C star. Okay. Oh, sorry. L intersection L2. L is equal number of A's and B's. That's right, right? Yeah. And L2 is A star followed by B stars followed by C star. Now L2 is regular, we know that, and equal number of A's, B's, and C's is non-regular. We've already shown that. We've shown that this is non-regular and L2 is regular. You've seen that, right? Just now. Now, what is the intersection? What is equal number of A's, B's, and C's? This could be something like A, B, 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 C, C. Or it could also be like A, B, C, A, B, C. Or it could also be A, C, B, C, B, A. And then again A, B, C. Anything like this is allowed. A's, B's, and C's could occur in any order. But what does A star, B star, C star say? A star, B star, C star says first A's will show up, any number of A's, then any number of B's will show up, then any number of C's will show up. Right? Now what do you have? You are looking at their intersection. What are the languages which are common between this and this? This is things like A, B, B, C, A, B, C, C, and so on. This talks about order, and this talks about number of elements, number of symbols. Number of symbols should be same. Number of A's equal to number of B's equal to number of C's. Their intersection will be all those strings that has A's followed by B's followed by C's. Additionally, number of A's equal to number of B's equal to number of C's. Right? Both the behaviors are combined. So what do you have? You have all strings of the form A to the n, B to the n, C to the n. B should be B should follow A, C should follow B, and their numbers should be equal. So that is the intersection. So what is this? What their claim is, it is ln. That is true. Ln, if you look at, is A to the n, B to the n, C to the n. So this part is true. Clear? This part is definitely true. Next, ln is not regular, therefore L is not context free. That's what they are saying. What is ln? Ln, this guy, is it not regular? Yeah, it's true, it is not regular. Additionally, it is not context free also. You may have seen it in the lectures that A to the n, B to the n, C to the n is not context free, whereas A to the n, B to the n is context free. Now the question is it because it is not regular? You can say that if you say that, oh, since ln is not regular, okay, ln is not regular, L is not context free. Can you say that? Ln is not regular, so L is context free. Can you say that? Such kind of a claim does not, we've never seen such kind of claim. So it's already, it makes sense to suspect this. It is kind of suspicious to talk about this way. And but ln is not regular. Say ln were context free, and we already know that this is context free, right? And intersection of context free languages is also context free. Then everything is well and good. So even though this was not regular, and it was, and let's say it is context free, okay, even though this is not regular, then everything is holding. It's all good. So it does not make sense to say L is not context free. Okay. So option. So there we have a contradiction. We have a, but if you are not convinced, we can look at the next option. Okay. Option D is not true. But finally, we'll look at this option. Okay, again, L intersection L2 is Ln, and Ln is not context free. Therefore, L is not context free. L intersection Ln, which is nothing but e to the n, b to the n, c to the n, which is nothing but Ln. Okay, and Ln is not context free. This is not context free. Therefore, L is not context free. Therefore, L is not context free. This is not context free. This means L is not context free. Now, does this make sense? Yes. Why? Because Ln is, again, to remind you, Ln is the a to the n, b to the n, c to the n, right? Which is, no, wait, not Ln here, L intersection L2, really sorry, L intersection L2. Okay, now L2 is defined as A star, B star, C star, which is regular. Now, if it is regular, it is context free also. What we know from the lectures is that intersection of CFLs gives a CFL. So if L is a CFL, then definitely Ln equals L intersection L2 is also a CFL because of this theorem, closure property, right? But that is not the case. But we are saying Ln is not context free. It is not a CFL. This is the question, right? So clearly there is a contradiction. Since Ln is context free, it must be that since Ln is context free and L2 is also context free, it must be that L is also context free. But Ln is not context free, okay, and this is L2 is context free, then L is not context free. Because if L was context free, then Ln would become context free, right? Because intersection of context free languages is another context free language. Okay, is that clear? Hello? Okay, so it's clear, right, Moana? Just let me know if you want me to repeat anything. Okay, so we'll look at the next another question in the previous week's assignment, and then we'll move to this week's thing. Okay. So here's the question. Okay, it's a simple question rather. So here's the question. S is so here's a grammar, okay, given to us. Okay. Okay, here's a grammar given to us. S generates, okay, S generates EXB and X generates DSC or DC. Okay, and okay, can you identify the variables and terminals here in this grammar? Oh, Akshay is also here.
Terminals A, B, C, D.
Terminals is A, B, C, D. Good. Variables?
Variables, starting variable S and X.
Good. Yeah. Starting variable and X. Okay, good. So let's move on. Consider the grammar G given above. Suppose the string S has a parse tree of height v plus 2, where v is the number of variables in this grammar. Okay, it should be in this, right? Is the number of variables in the grammar. Which of the following statements are true? So firstly, we have this is equal to 2. Number of variables in this grammar are 2, so the cardinality of v is 2. Okay. So now it says, suppose a string S has a parse tree of height v plus 2. You've all seen what a parse tree is, right? It looks like this. You know, you have a production S, and after S you get, say, X, AXB, and from X you get something else, and so on. What we have is the height of the parse tree is size of v plus 2. Okay, and what is size of v? 2 plus 2, which is equal to 4. 4 is the length of the parse tree now, height of the parse tree. Okay. Now what are they saying? They are saying the length of the string is at most 2 to the size of v plus 2. Okay, that is one thing. Next is there is a path from root to leaf in the parse tree that has the variable s occurring twice. Next, a path from the root can only contain unique variables. Next, the length of the string is v plus 2. So let's see. X could generate DC, but if X generates DC, okay, if you look here, X could generate DC, but if X generates DC, then our computation has stopped. Our output is A, D, C, B, right? But the height is not 4 here. Height counted with the number of edges, okay, not the number of nodes. So okay, yeah. So X cannot be DC. X cannot generate DC. It needs to generate something to give a greater height. So it needs to generate DSC. Okay. Now since we have an S here, we can always generate more height. Now S will again generate A, X, B, because that is all that it can generate, right? Now what is the height? The height is 3. X can only generate now D and C. Okay. So firstly, there is a path from root to leaf in the parse tree that has variable s occurring twice. That is always the case. Oh, one more it needs charge. As you can see, that is always the case. Because there are only two. In other words, this can be seen as an application of pigeonhole principle. There are v plus 2 many, more than v many variables in the height of the parse tree, right? In there is some path, which means there is some path of length v plus 2. And how many variables are there? Only v many. So obviously there should be more than one in the path, more than one variable in the path, right? So okay, I think got charged a bit. So occurring twice, that is true. A path from root can only contain unique variables. Is that true? No. I encountered X, then I encountered S only. It's not unique. Unique meaning encountered only once. Okay. This is clearly false. The length of the string is uh, size of v plus 2. Is the length 4? V plus 2 is 4. No. Because our output is A, D, C, B, C, B. Right. What is the length of this? 1, 2, 3, 4, 5, 6, 7, 8. 8 is the length. So this is not true. Our length is 8. The length of the string is at most 2 to the size of v plus 2. Is that true? 2 to the size of v plus 2. What is 2 to the v plus 2? Which is 2 to the 4, which is 16. We have 8. 8 is at most 16. So the answer is yes. So A and B are true and the remaining two are false. But take note that there is nothing special about the number of variables being 2. Okay. We can actually, I showed this, right? But we did not show this actually. We can just look at, we can use just what is called the pigeonhole principle in discrete maths. We can just look at the fact that, oh, okay, the height of the tree is very big. Okay, height of the tree is very big, much larger than v. So in any path, there must be more than v variables encountered. So that will give us most of the thing. And next is that, at every level, it is having at least 2 children. So the leaves of the tree, okay, the leaves of the tree is, if you take like a binary tree, it is always 2 to the n, the number of children, where n is the height of the tree. So you can always say that, oh, okay, the maximum number of children it has is 2 to the n. So therefore, the number of the length of the character generator is at most 2 to the height of the tree. That is another way to argue. But here, since they are giving us an explicit example where there are 2 variables exactly, and this is how it behaves, we can analyze it further and say that, oh, okay, this is the longest string that this particular string is the longest that this grammar can generate. So that is another thing. That is another way to argue this. Okay, good. So okay, I hope that was clear. It was not something too abstract. So I hope that was clear. So yeah, let's move on to this week's content now. Okay. So this week's content is Turing machines and decidability. So we've seen machines already, right? What are the kind of machines we've seen? We've seen a DFA, finite automata, or an NFA. And we've seen PDAs and non-deterministic PDAs. And we showed that these two are not equal in power, but these two are equal. DFAs and NFAs are equal. And there are some kind of models in between also. But this time we are only focusing on one, that is Turing machines. Now, quick recap. Here what do you have? You don't have any memory, or you have very little memory. Constant memory. That is, you use states to remember. You can do simple tasks like modulo operations, right? And you can do regular expressions and so on, where you need just constant amount of memory. That means you just remember what state you are in, and that much memory is enough for you. What we want to do is we want to generalize the model, give it more memory, and see what happens. So PDAs and PDAs are one such generalization. Here it can be seen as a DFA with a stack. And 2 weeks ago in the assignment, we saw that what happens when you give a queue instead of a PDA, right? Queue instead of a stack. What happens, and what happens if you allow only scanning once, and so on. There are different questions you can ask. But this is, you give it a memory, but you don't give full access to the memory. It needs to be read in a certain order. That is what a stack is, right? It needs to be read in a certain order. And finally, you have Turing machines, which are um, infinite length tapes. Okay, so Turing machines are, you can think of a machine M with a head. What is it's called? A head is a pointer, and there is an infinite tape. Okay, you can consider a one-way infinite tape, but it is equivalent to a two-way infinite tape. You can have infinite length on either sides, and there are cells, okay, which are capable of storing your tape alphabet, which are taken from gamma. Okay, and you are allowed to perform reads and writes. And Turing machines may also be defined in different ways, but most of the ways are equivalent to each other. That is, uh, main important thing to know is that Turing machines with not infinite, sorry, multiple tapes, Turing machines are as powerful as single tape Turing machines. Okay, Turing machines with multiple tapes are as powerful as single tape Turing machines. You've already seen that, and you saw the Church Turing thesis. Which says that any computational process, any physical computational process can be done by a Turing machine. Okay. So what does it mean? It means that any computer that you can think of, okay, any phone or laptop or whatever, Turing machine is as powerful as that. So Turing machine is not a weak model. In fact, Church Turing thesis says that uh, you cannot actually build a machine which is more powerful than a Turing machine. By power, we don't mean speed. Okay, by power we mean the ability to solve problems. In other words, the ability to decide languages, recognize and decide languages. So, but this is a vague thing to say. Okay, so you cannot have a very formalized proof for this. Hence, it is not called a Turing machine theorem, Church Turing theorem or Church Turing lemma or whatever. It is called a Church Turing thesis because this is something that cannot be proved, but it is believed to be true. Okay, and therefore it also means that any algorithm you can write, okay, any algorithm that you can write, you can do it by a Turing machine. So when you think of Turing machines, I just want to make this small remark that when you think of Turing machines, please don't restrict to the view of the tapes and making marks here and there and so on. You can abstract it out to algorithms. Okay, so you can write description of Turing machines as if you are writing descriptions of algorithms, and since they are equivalent by the Church Turing thesis, it is always fine to write them as algorithms. Because in DFAs we were thinking of states, moving from one state to another. Turing machine, you don't really need to think of it in terms of moving to one state and another. There is people also teach in this way, right? Where move from left to right, and then right when you see an A, write a B, and then move from left to right. So this is a very restricted view about it. When you try to solve harder and harder problems, this becomes very complicated and low level. So it's like coding in binary or assembly. So think of just your regular algorithms, pseudocode or C programming or something like that. Okay, and that will always help. Okay. Now, finally, the main topic, okay, is about decidability. Decidability. Okay. So, what is decidability? Uh, a language L is decidable if there is a Turing machine that accepts it. The Turing machine, let me call it M, such that M always halts. In other words, it never loops. Loops meaning infinite loop. Okay, you don't keep needing to wait for an answer. Okay, so any input, on any input, let's say I give a machine M, it will never happen that it keeps looping, infinite looping, and it will never give me an answer. It will never happen. It will always give me an output given an input. Okay, then if such a Turing machine exists for the language which accepts all the strings in the language, then then the language is called decidable. Furthermore, such a Turing machine that M always halts, such a Turing machine is what is called a total Turing machine. Okay, let me not duplicate. I think copy is better. Cut. Yeah, now we solve some problems. Okay. Yeah. Okay. Great. So the question says, are the following problems decidable? Given the description of a Turing machine, M, can you test whether there is an equivalent machine with an even number of states? This is the question. Whether this problem is decidable or not. In other words, you can interpret it as a language. What will the language be? It will be the set of descriptions of all M. Remember that this is a string, and in the lectures you've seen that any Turing machine can be written as a binary string, right? Now, okay, a string M that represents the description of M, okay, such that there exists a Turing machine M with even number of states. So, any guesses? Would it be decidable or undecidable?
Decidable, sir.
It is decidable. Okay, good. Why? Any any reason you think?
Turing machine accept the given.
A Turing machine?
Turing machine accept the given string, sir.
Turing machine accepts even string.
Yes.
But here I'll slightly explain this further.
Okay, sir.
The what we need to decide is given is a Turing machine M, okay, and it description of M. Okay, it's a string and it's a description of M. You want to tell, okay, if there is a Turing machine N. Oh, okay, I got what you're saying. Okay, you want to tell whether there is N such that it has even number of states. Okay, and what you meant to say was you look at the description and check whether there are even number of states or not. Hmm? you look at the description, and because what is contained in this description, it'll be like sigma, uh, delta, sorry, gamma, q, final state, start state, blank symbol, whatever. So you look at this and just look at q, okay, and count the number of states and tell whether it is even or not. So is that what you meant, Bhuvan? Or is there something else?
Yes, sir. That is a Turing machine already.
Yeah.
The state says that there will be equivalent machine.
Right. So if that, yeah, that is one thing. So if you look at the description and you observe that there are even number of states, then you can definitely say yes, there is a Turing machine which accepts the language, okay, which accepts the same language which has even number of states. That is true. But the question is now, what if this turned out to be odd?
If M
What
is not
Yeah.
Turing machine not accept.
Oh, but how do we say for sure that we can never build a Turing machine accepting the same language with even number of states? How can we say that we can never build another Turing machine? So if you look at the question, whether there is an equivalent machine, or in other words, another machine which accepts the same language, okay, with even number of states. Getting at what I'm saying?
Can you repeat, sir?
Yeah, what I'm saying is, okay, what I'm saying is the problem is, given a Turing machine, we want to check if there is an equivalent machine, which means another machine, okay, another Turing machine that accepts the same language. Remember that every language need not have a unique Turing machine. Okay, for a single language, there may be multiple Turing machines that compute the same language. Okay. Now, I look at the input, which is m given to us, and I count q. I count the number of states, and the number of states turned out to be even. Then I say, okay, yes, there is a Turing machine. Okay, not another, some Turing machine. Okay, yeah, not another, some Turing machine that accepts the same. Then we'll say, oh yes, this machine itself is a machine which will accept the same language and has an even number of states. Then we'll say that yes, when it is even, when this is even. But what if this is odd? Now, like you said, if this is odd, then we'll say no. But how can we guarantee that there will the m has odd number of states? That is fine. But how can we guarantee that there does not exist any other machine which will compute the same language? You get it now? What I'm trying to say?
Yes, sir. Already they have told that. Commonly, they have told that Turing machine.
Yeah.
Accept that the first statement. The machine.
Hmm.
Then if it is accepted, definitely it may be a odd number or even number.
Yeah. Sorry, I cannot hear you properly. Can you say again?
In the statement, sir, question statement.
Say it again.
Can you show me this, sir?
This is the channel is noisy, so I cannot hear you properly.
The question they have mentioned that the language is accepted by the Turing machine. It may have a odd numbers or even numbers, but it is accepted.
Yeah.
And if it is accepted, it is decidable also.
Right.
It may odd number. It may consist of odd number of states, or it may consist of even number of states.
Right.
That is a statement.
It may have an odd number of states. Okay, it may have an odd number of states, and there could also exist a Turing machine which has an even number of states which accepts the same language.
Yes.
But how do I do that? how do I make another Turing machine that accepts the same language but with even number of states? Now I'll tell you. What you do is take the same machine, okay? Take machine M, okay, and it has an odd number of states. What I'll do is simply add a dummy state. Okay, dummy, what do I mean by dummy? Unreachable. Getting it?
Yes, sir.
So if I add a dummy unreachable state to this machine, my resulting machine will have how many states? Odd number of states. It already had odd number of states. I'm adding one more state which can never be reached. Yeah?
Even number. It will give even number.
Exactly. Even number. And does it affect the language computed?
Yes.
Does the language computed change?
If we include the dummy, it get halted, sir.
No. Halting. M was already halting. Okay, or it doesn't matter whether M was halting or not. I'm just saying L accepts a set of strings. Okay.
Okay, sir.
A, B, C, B, C, D, and whatever. That is what M accepts. If I add one more state to it, which it is not, I'll explain using a DFA. Okay.
Okay.
Let's look at the DFA accepting A star, B star. Okay. So what does the DFA look like? Here is the empty state, and if I see A's, okay, then I loop, okay, and or let's not even do A star, B star. Let's just do A star. This is a DFA accepting A star. Right. What happens here? It sees an A and it keeps seeing an A, it will still accept. Right. And if it sees a B anytime, then it will go to a dead state. Correct?
Yes, sir.
This is the language. Okay. What is the language? A star. Now what I'm saying is, let me add another state to it. Okay. I'll call this state 1, I'll call this state 2, I'll call this state 3. Okay. And this state does not have any arrows coming to it. So if it has no arrows, it is what are called unreachable. Or it is also what is called a useless state. Because no string can actually encounter this state. Okay. Now tell me, is this DFA accepting any more strings than it used to, or any fewer strings than it used to? Is the language of this DFA changing when I added the state?
No, sir.
No, right?
Yes.
Because this state is unreachable, it is useless, it is not doing anything.
Yes, sir.
Similarly, to this Turing machine M, which had odd number of states, I added this unreachable state. Okay.
Yes, sir.
And no string will ever reach this, because there is no definition in the transition function that says, oh, go to this particular state, let me call it D, go to this particular state. It is never saying that, so there is no string that reaches it. So if M was accepting a language L, what will this bigger machine accept? This bigger machine with this unreachable state. It will still accept L, right?
Yes, sir.
Right? So now the question of whether given a Turing machine, can I build another Turing machine that has even number of states, will always be true.
Equal number of machine with even number of states.
Even number of states will always be true. Why again? Because if it already had an even number of states, then like you said, I'll just say yes, because itself it is an example of a Turing machine with an even number of states,
Okay.
right? But if it was odd, what I'll simply do is I'll add this dummy state and make it even number of states,
Yes, sir.
and then the language computed is same, and therefore it is always true. The answer is always true for this problem. Sorry, answer is always yes for this problem. So what is algorithm? The algorithm or the Turing machine. What is the Turing machine that does this? It takes as an input a machine M. It will just output yes and halt. And since this Turing machine halts always, this is a total Turing machine. And the problem, so the problem is decidable. Okay. Okay.
Yes, sir.
Okay. Good. Okay. I'll write here. The key idea is that it is always possible to come up with even number of states. Okay. Okay. So this is slightly of a higher difficulty. Okay. And here's the question. Is it decidable, given a description of a Turing machine, whether the 42nd cell in the tape is ever touched? Okay. So given M, okay, the problem is as follows. Okay. Problem is as follows. Input is the description of a machine M. Output is yes if there is an input such that M touches the 42nd cell and no otherwise. So this appears to be undecidable. Okay. Why? I'll tell you. This appears to be undecidable. Why? I'll tell you. Because here, this is what we need to do. Okay. So this is the input M. So if I run over the, let's say over 0, I run. Okay. I run the machine over 0. And it moves here and there, the head pointer moves here and there until it finally touches 42. And I say yes. But what if it did not touch 42? What if it never touches 42? 0. Given 0. I'll give a 1 now. Yeah?
Maybe looping.
Yeah, it could loop. Right? It could always loop. And what if it loops inside here only? Getting it? What if the tape? What if the head pointer keeps moving left, right, left, right, left, right, but it never touches the 42nd cell?
Yes, sir.
Then I'll just keep waiting for the machine to reach the 42nd cell, no? And that will never happen. That will never happen because the machine is configured in such a way that it will always loop here. Okay. And therefore I would say that, oh, okay, any Turing machine that needs to solve this problem cannot be total. It cannot halt, because if the Turing machine takes the input and simulates it, then we'll keep waiting until the 42nd cell is touched. But what if it loops before going into the 42nd cell? Okay. Okay. Sorry. Ever touched on input, let's call it 101. Sorry, this is a full question. On input 101. So I input 101. What if on input 101 it keeps going back and forth within the first 42 cells and it never touches 42? My Turing machine will keep waiting for it to touch 42. Is the problem clear?
Yes, sir. It is undecidable, sir.
Yeah. Wait, well, it appears undecidable. That is what I want to say. It appears undecidable, but surprisingly it is decidable. Surprisingly. Okay.
Okay, sir.
Why? Yeah.
What,
Yeah.
sir? Yes, sir.
Okay. Okay.
Why?
Yeah.
Um,
Hmm.
that is, it is a loop, sir. It goes on looping.
Hmm. Yeah. The question is, can we detect the loop? Can we detect that it will go in an infinite loop?
No, sir.
No. Why? It, it makes sense to say no. That is true, because if you could detect the infinite loop, then I mean, it would be like the problem, the halting problem itself would become decidable. But the main thing is, this is the answer here. Okay, the 42nd cell. Akshay, are you with us? Are you with me?
Yes,
Um,
sir.
Yes, sir. Yes.
yeah. Okay. Okay. The the fact that I'm bounding the length of the tape to 42 is the key here. Okay, is the key here. So what is the bad case? Okay, what is the good case first? Run M on 101. Okay, that is what the question is. Okay, whether it will ever touch the 42nd cell on input 101. That is what we need to test. Okay, run machine M on 101. Okay, this is what our supposed total Turing machine will do, and M halts. Okay, after touching cell 42, then output yes and halt. Okay, good. This is a good case for us. Okay, it keeps going. We simulate and it touches. Oh, it touches the 42 cell. I'll output yes. Okay, it touches the 42 cell. Good. But another thing is M halts before touching cell number 42. Okay, so I'll call this 0, 1, 2, 3, and so on till 42. Before touching 42. So since M never touches 42, cell number 42, so it will output. Then we need to output no, it never touches 42. Now, what is the bad case? What is the case that we are not handling? M loops. Okay, M loops. Okay, M loops also while looping. Okay, while looping, M touches 42. While looping, M touches 42. This is also good for us because since we ran M on 101 and we kept checking. Okay, we kept checking. Um, it is guaranteed to we are guaranteed to see a case when M touches 42. For example, okay, I run M on 101. So it is looping, but it is touching 42 also. It is touching 42 also. So this is a good case. This is still a good case. Then output, that's not right, M loops. Here. Okay. M touches, then output. Yes, it touches. And then we'll halt as soon as it touches the 42 cell, 42nd cell. Now, what is the bad case? M loops on input 101, okay, and never touches cell number 42. This is the worst case for us, because once we run the machine M on 101, we'll keep waiting and waiting and waiting and waiting and waiting. Okay, but it will never touch 42. This is the bad case. Question is, how can we detect? Okay, how can you detect this? The answer lies in the number of configurations. Okay, number of configurations possible. I'll quickly touch on what configuration was. If configuration is the current status of Turing machine. Okay, what does it contain? Okay, current state, which state you are in. Okay, head position. Okay, and head position and tape content.
Tape content.
Yeah, current state, head position, tape content. Okay, now if observe that if my Turing machine has infinite tape length and it loops infinitely, then there are infinite possibilities for the configuration to have. Head position could go infinitely wherever it wants. Tape content could also have infinite number of possible strings, and current state, this is at least finite. This is finite. Okay, so it'll look something like, okay, configuration looks something like, okay, Q0, I am at state Q1, sorry, not Q0, let's say Q1, and head position is at 21. This is the head position, and what is here, this is the um, tape content 10110. This is what it looks like. And then what can happen on the next step 2, it could move to another configuration, Q2. Head position, it could move left or right. Let's say it moved left. Okay, it moved left and it went back to 20, right? And tape content, it is still 10110. And then on step 3, the Turing machine configuration changed. It changed to Q3. Okay, and it went to, let's say, right again. Okay, the cell, in the cell, this is 20, this is 21. It moved from 21 to 20 and moved from 20 to 21 and so on. And let's say tape content changed 10111. Now it has become. Okay, so something like this. This is what happens inside. Question is, how many possible configurations are there? Okay, how many possible configurations are there? Well, number of states. The first, if the number, if Q is represents the set of states, then the number of possibilities here are only number of Q, the size of Q, right? Times how many possibilities are there in the head position?
3.
Yeah. Oh,
3.
you by head position, Bhuwana, I don't mean left, middle, right. I mean 0, 1, 2, 3, 4. What is the position in the, getting it? 0, 1, 2, 3, and so on. That is what I mean by head position. Okay.
Okay.
So how many possibilities are there, Bhuwana? How many possibilities are in this place? if it was left, middle, left, stay, or right, then it is 3. That is correct. But if this is what I mean by head position now, what do you think should be the number of possibilities?
I think both left and right side we have a equal possibility, sir.
Yeah, but no, but head position, I'm telling you, it does not mean head position does not mean left, right. Head position means, and it is an integer. It tells where it is the position cell number. It is the cell number. Okay, which cell we are in. Whether we are in 20, whether we are 21, whether we are in cell number 3. That is what the head position says.
21.
So yeah, 21, 20, and so on. So how many possibilities are there?
2 possibilities, sir. 21, 21.
No, I mean that is in the example I gave. But for a general Turing machine, what is for a general Turing machine? What is the length of the tape? For any Turing machine, what is the length of the tape?
Infinity, sir.
Infinite, correct. So how many head positions are possible on the tape? Like how many cell positions are possible on that infinite tape?
Again, it is infinity.
Again infinite. Good. So how many possible configurations? Well, q times some natural number, right? Which represents the size of natural number. Okay. Times the tape content, which is also 2 power infinity, some 2 power sigma star. Or sorry, size of sigma star, which is also infinite. Which is also infinite. This is the tape content. Possible tape content as sigma star, right? Right? There are infinite possible tape head positions, infinite possible tape contents. Right? Let me know if there is a problem. Yeah? Hello?
Yes, sir.
Yeah. This is fine, right?
Yes, sir.
Okay. Now is the interesting thing. Okay. But for our case, we are saying the machine will never go outside the 40-second cell. For this particular case, the bad case, M loops on 101, never touches the cell number 42. If it never touches the cell number 42, if it does not ever touch the cell number 42, the head position, the number of head position is bounded now. The number of head positions are bounded. What are the number of head positions possible? In this case,
If it is not adjusted with 42, then 41, sir.
it could be 41, it could be 40 also.
Yes, sir.
It could be 39, 1, 2, 3, 4, whatever until 41, right?
Yes, sir.
It could be anything besides 42.
Yes.
And above 42.
Yes, sir.
Right. So in this case, I need to charge. Just give me a moment. I need to charge my. Okay. Yeah. So yeah, it could be in this case number of possible head positions could be it could be 0, 1, 2, anything till 41. So there are 42 possibilities for the configuration. Okay, and the tape content, the tape content, the my in my head never moves past 40-second cell. Head never moves past 40-second cell. So I cannot modify any content here. These are all blanks. So what is the only possibilities for my tape content? This area, which could be either 0 or 1. So this area, which could be either 0 or 1 or whatever. So how many possibilities are there? But 2 to the power 42. Getting it? So this infinite number of configuration is now finite for us. Now number of possible configurations is equal to number of states, which is already finite, times number of head positions 42 times number of possible tape contents 2 to the 42. This is the maximum number of possible configurations I have. Since my head is never moving away from the 42nd cell only. Getting it? Since I'm not moving past the 42nd cell, the head positions, okay, number of possible head positions is bounded by 42, and the number of possible tape contents is also bounded, because I cannot write on a cell that is past 42. So the length of the string is at most 42. So how many number of strings are there which is of length 42? Well, 2 to the 42. So this is the number of configurations. Now the final observation is that if any configuration, if there is a loop, there is an infinite loop, some configuration is repeated. Getting it? So run my Turing machine for q times 42 times 2 to the 42 steps. If 42nd cell is still not touched, then, because if it means it takes more than this many steps, it means definitely I've entered a loop. Okay, then output yes. Are you getting this?
Yes, sir.
Right. So even what is the lesson here? Even though it might seem deceiving for us, okay, even though it might seem deceiving that this looks like an undecidable problem, because I'll just keep waiting and waiting and waiting and waiting and I'll never get the answer. There are actually clever ways to design decidable total Turing machines. Okay, so I would recommend looking into this particular problem once again. So okay, we'll move on to the next one. Akshay, is it clear?
Yes, sir.
Okay, good. Okay, so guys, let me know if anything you want to ask. Okay. Okay, so we'll quickly look into these questions. Okay, I'll do the first one. Then the remaining, please tell me what some suggestions. Okay. So here I'll demonstrate the first one. Show that the following language equals, which takes a description of M. This denotes the description of Turing machine M. Okay, and such that M is a DFA that accepts some string with equal number of zeros and ones. Okay, so it is saying some string, okay, not all strings. Okay, equal number of DFA which accepts some strings with equal number of zeros and ones. Again, I'll repeat. Example, M is a DFA with language, say 0 1 1 1 0 1 1 1 1 0 1 0 1 and so on. Then answer is yes. My total Turing machine should say yes when given this DFA as an input. Why? Because this guy has equal number of zeros and ones. Okay. Okay. What is the problem here? What is the problem? Okay. Problem. Simulating. One direct approach is what? I take one possible input, let's say 0. I put it through the DFA and simulate it, run it on 0. Then I wait and it'll give me the answer. Then I'll do 1. And then it'll run on 1 and then give me the answer. Then I do 0 1. Then on 0 1 it'll run and give me the, okay. And so on. And okay, so let's say problem, this is the simulate on, let's say 0 1 0 0 1 1 0 1 0 1 0 0 1 1 0. Okay, 0 0 1 1 is already done. 1 0 1 0 and 1 1 1 0 0 0 and so on. All these strings have equal number of zeros and ones. I'll simulate it on all strings that have equal number of zeros and ones. If DFA accepts, then accept. But what if, problem is, what if there does not exist a string in the language of M, language of the DFA, such that there are equal number of zeros and ones? What if there is no string in the language such that there is equal number of zero? That means the DFA will never accept it, any language, which means DFA never accepts. So this simulation will never end in that case. This never halts when DFA does not belong to equals, or machine M, description of machine M does not belong to this language equals. When the machine will never accept a string which has equal number of zeros and ones, this simulation will never run. So does that mean it is undecidable? Well, there is a more clever way to do this. Okay, there is a more clever way to do this. And look at this technique carefully. Okay. What I'll do is, I'll take a DFA, not a DFA, take a PDA, okay, accepting one moment. One to the no, there's a problem with this actually. Okay, I'll slightly modify this question. Okay, equal number of zeros and ones. um, ones follow, sorry, where zeros followed by ones. Okay, where zeros are followed by ones. So okay, now let's try PDA. So take a push down automata accepting 0 to the n, 1 to the n. Why is there a push down automata? Why is there a push down automata? Because 0 to the n, 1 to the n is a CFL. This is a CFL, context free language. So a push down automata always exists for this. So what do? I will construct a um, construct a PDA, okay, such that it accepts, okay, let me call the PDA n, okay, I'll call it n. It accepts the language of n intersection the language of m. This is the PDA, this is the DFA. How do I do this? Using subset construction. Okay, construct a PDA which accepts the language of n intersection language of m using subset construction. Why can I do subset construction on a PDA and DFA? Because DFA is also a PDA only. So the same same mathematical definition will still apply. Okay. So DFA is just a PDA that does not use a stack. Okay. So using subset construction, I got this. And I will call this machine mn then new n. Okay, not n, new n. PDA m new. Let me call this m new. Okay. Now what I'll do is, if m, okay, accepts a string of the form 0 to the k, 1 to the k, okay, any string of the form 0 to the k, L of n intersection L of m, okay, which is nothing but L of n new. What will be the intersection? So this accepts 0 to the n, 1 to the n, and this accepts some arbitrary language. Okay, but we know that m accepts at least one string of the form 0 to the k, 1 to the k. Then L of n intersection L of m will definitely contain L of k, 1 to the k, 0 to the k, 1 to the k, because this string is common between them. Getting it? But if no such string of the form 0 to the k, 1 to the k is accepted by m, then what will the intersection be? Since there is no such string which L of m accepts, and L of n always has strings of the form 0 to the n, 1 to the n, or 0 to the k, 1 to the k, their intersection is empty. Okay. No such string exists, then their intersection is empty. So therefore you almost have your answer. What you need to do is, you need to remember that this PDA, which was done in the lectures, okay, that is checking if PDA language checking if language of PDA is empty or not is decidable. So here too we are doing the same thing. No, if it does not accept a string of this form, then the language is empty, the construction is empty. And if it does accept a string of the form 0 to the k, 1 to the k, then the language is not empty. It has 0 to the k, 1, at least 0 to the k, 1 to the k. Getting it? So what is the final answer? The final total Turing machine is as follows. Construct M new such that language of M new is the intersection of M and N, intersection of the languages. Okay. Now, check if language of M new is empty. Check if the language of M new is empty, and if it is empty, then output. If it is empty, then there is a common M accepts a language of the form 0 to the k, 1 to the k. Output no. Oh, sorry, just the opposite. If it is not empty, then it accepts. And else output yes. And this thing is nothing but same as ePDA, checking whether the checking if the language of PDA is empty or not. It is decidable, and this part is decidable, and this part is also, it will never halt. It will always halt, and these parts will always halt. So this machine always halts. So language of this question, the language in the question equals is decidable. Okay, to repeat what I've said, we want to check whether the given a DSA, okay, is it true that it accepts a string of the form 1 to the 0 to the k, 1 to the k, okay, or in other words, I also said equal number 0 is 1 where zeros are followed by 1, which simply means 0 to the k, 1 to the k. So what did I do? I took a CFL, which is CFL. What is the name of the CFL? What is the language? 0 to the n, 1 to the n, and we know this is a CFL, so it definitely has a push down automata for it. What I'll do is I'll construct a new push down automata that accepts the intersection of the DFA, of the language of the DFA that I have, and the and this new this push down automata computing 0 to the n, 1 to the n. If it so happened that the machine M accepted a string of the form 0 to the k, 1 to the k, then the intersection definitely would have been non-zero. Otherwise, their intersection would have been empty. Otherwise, meaning M does not accept any string of the form 0 to the k, 1 to the k. Okay, then the resulting language of the intersection would have been empty. And if it is empty, then we would output no. And if it is not empty, then we would output yes. Checking whether the language of a PDA is empty or not is nothing but what is called ePDA, and ePDA is decidable. That is what we saw in the lectures. Okay. So is it clear, Bhuwana and Akshay? Or was this
Yes, sir.
clear, right? Okay. Bhuwana?
Yes, sir. I have understood partially, sir.
Okay. Definitely, if you see the next one, you'll fully understand. Okay.
Okay, sir.
Okay. So here's the next one. Okay. Here's the next one. Oh, we have some time left. Here's the next one. Okay. Similar flavor again. I want to come up with a push down automata or a DFA and finally do an intersection and then talk about their emptiness. Okay. Here is the question. Given a machine M, check if the DFA ever accepts a palindrome or not. Okay. So I want to do again L of M intersection. I want to construct a PDA such that want to construct PDA such that L of M, language of my new PDA, M new, is language of the machine, language of the DFA given to us, intersection, language of N. Okay. Now, what should this language of N be? That is the question. Okay. And why do I need this? So that when LM contains a palindrome, when LM contains a palindrome, language of M contains a palindrome, this language of M new, that is the intersection, is non-empty. And L of M does not contain palindrome, then L of M new is empty. If this guy contains a palindrome, then this entire thing should be non-empty. The resulting set should be non-empty. And if it does not contain a palindrome, no palindrome here, then their intersection should be empty. So any idea what L of N should be? What should L be? Okay, L of N be, so that when this accepts a palindrome guy, okay, this guy accepts a palindrome, then their intersection, these two, the intersection is non-empty. It will contain something. And if L of M does not contain a palindrome, then on intersecting with L of N, my set is empty. Think about it. Compare with what we did previously. It's quite logical also. Any idea? Okay, I'll let you know. This set L of N, I'll take it to be exactly the set of all palindromes. If it contains all palindromes, if L of N contains all palindromes, then if L of N contains even one palindrome,
Sir,
yeah,
this I have understood, sir.
this you understood, right? Getting it?
Yes.
So if you take it, good. So if you take this to be the set of all palindromes, even if this guy has at least one palindrome, their intersection, there is one common member, there is one common element, and therefore M new is non-empty. It contains at least that particular string which is a palindrome which M accepts, okay, which is contained in L of M. Now, if L of M does not contain any palindromes, obviously it has nothing in common with this set, right? Because this guy is only consisting of palindromes. So obviously L of M new is empty. Okay. So, right. Now the question is, why is this a PDA? Why is N a PDA? Well, because the set of all palindromes is a context-free language. Why? Well, you can generate a grammar for it. You can do this is the grammar for it. S B, or if you take binary, 0 S 0, 1 S 1, 0 1, or epsilon. So this is a grammar that generates palindromes, like 0 S 0, 1 S 1, 0 S 0, epsilon, or 0, let's say. So 0 1 0 0 0 1 0. This is a palindrome. So this grammar will only generate since there. Okay, let me write it better. Since there is a CFG, that means a CFL. That means also a CFL. There exists a PDA accepting this grammar, which is nothing but a set of all palindromes. So a PDA exists, and this is what I'll call this L. Now again, I do the same business